Tēnā koutou katoa, kua tae mai nei I tēnei rā ki te tautoko I te kaupapa o te wā, ko Karen ahau, e mahi ana ahau hai Pukinga Huringa Āhuarangi ki te kainihera o ngā Rotorua. Tēnā koutou, tēnā koutou, tēnā koutou katoa. So, hello everyone. My name is Karen. I am a climate change analyst for Rotorua Lakes Council, and this is a series that I put together called Climate Kōrero. This particular talk it's kind of like Climate Change 101. What is climate change? How is it? Why did it happen? What causes it? And in some terms that you may be familiar with or not. It's a brief explanation of climate change in some terms. Okay, getting started. So you might notice in this country we have a problem with water. Last summer, if you can even call it a summer, we had a lot of rain come down Auckland, flooding in Auckland, and then just a very short time later we had a lot of rain come down the East Coast, massive flooding. But if you rewind only 12 months, we were in the middle of a drought. So not enough water. We had a serious drought in Northland. The reservoir levels in Auckland were getting pretty low. We had quite serious bushfires around Nelson. So that was just 12 months in this country. If you look elsewhere in the world, it's pretty extreme. Pakistan, a third of the country was underwater. We had serious droughts in the northeast of America, heat waves. Yeah, every time you look at the news, it feels like there's something dire happening about too much or too little water. So why is this? And it's really to do with temperature. And since about 1880, we could measure temperature. And so that's what we've done. All around the world, we measured the temperature. And this red line, if you look at my cursor, is the direct measurement of temperature that we have done all around the world. And then when we got a bit smarter from like the 1950s onwards, we could measure temperature indirectly. So temperature of time gone past. And that is through tree rings or coral or ice cores. And so we've got this good idea of what temperature's done for the last 2,000 years. And this axis is the change from pre-industrial time. So this term is used a lot. And the industrial era was really a time when mankind had quite a big influence on our environment. And prior to that, we didn't. So we often talk about pre-industrial. So this is the change from pre-industrial. So you see it hasn't changed a lot. It's been sitting around zero, slightly lower, and then suddenly it shot up. And now we're sitting at about 1.3 to 1.3 degrees above pre-industrial time, which doesn't seem like much, eh? 1.3 degrees, it's a bit warmer winter, a bit warmer summer, but that has quite a huge impact on our water cycle. For instance, if you have increased temperatures hitting the ground, then you get more evaporation of water from the ground. So it's harder to grow stuff. Your crop doesn't grow as well if you don't have as much moisture, enough moisture in the ground. If you've got more evaporation, then stuff's drier, so it burns really well. So you've got more bushfires. If it's a bit hotter, you get less snow and ice forming, which is a bummer if you like skiing. But if you have, for instance, a glacial-fed hydro dam, then that's a problem for your electricity. So you've got this increased temperature causing this evaporation. This evaporation goes into the air, and then when it gets cold, it comes out again as rain. And so you've got more rain now. So when it rains a lot. So you can have things like flooding, you can have things like landslides, you can have stuff washing into your drinking water supply causing contamination. And that's just looking at what is happening on land, but a lot of Earth is ocean. And so that increased temperature hitting the ocean means that the oceans are getting a bit warmer. And when water warms, it increases in size, it expands. And that means that the level of the sea goes up a bit. And then you've got your warmer oceans, which will cause ice that is sitting in that water to melt a bit faster. So in the North Pole, we have the Arctic, and we're having a loss of sea ice in that northern region. We also have another issue amongst so when we have a storm, it sits in the tropics because that's the kind of warm part, and the warmth gives energy to that storm. So those tropical storms tend not to go too close to New Zealand. But with a warmer ocean, those tropical storms are hitting our shores, which is unusual. Okay, so that's just some examples of what increased temperature can mean for us. So why is temperature going up? Well, it's to do with the atmosphere and the gases in the atmosphere. So the atmosphere is just like a really thin layer of gases held closely to Earth. The majority of the atmosphere is made up of nitrogen, 78%. 21% is oxygen. That's good. We need that. And then the rest of the few percent is made up of a lot of different gases. And some of those gases are known as greenhouse gases, the main one being CO2, carbon dioxide. And a greenhouse gas is pretty self-explanatory, really. It acts like a greenhouse. So you've got the energy of the sun hitting the earth, and then you've got your greenhouse, your roof, which is effectively stopping the heat from going back out into space. And if we didn't have any greenhouse gases, Earth on average would be really cold. It would be about minus 18 degrees. So it's good that we've got some greenhouse gases. But the problem is how much we have. I've got another graph. I like graphs, obviously. And this is the carbon dioxide concentration in the atmosphere for the last roughly 1 million years. This is quite cool, so I'll tell you. So when you've got snow falling, that snow sort of lands on the ground, and there's a lot of air trapped in that snow. And then over time, it compacts, compresses, it forms ice. But you've still got that air in the snow, or the ice now. And so what they do is they just drill it out, and then they analyze all those tiny little pockets of air, and they can see what the atmosphere looked like when that snow fell a long time ago. I think that's pretty cool. So what they found is that for the last roughly 1 million years, the concentration of CO2 in the atmosphere, and so ppm is a unit of concentration, it means parts per million, so 1 part of something to 1 million parts of something else. And it's been sitting at like 170 to 300, bouncing around up and down, up and down. And then suddenly it shot up. So it's currently sitting at over 400 parts per million. And why is this? Well, the reason has to do with fossil fuels and us burning fossil fuels, us humans. So we've built our industries, our cities on a foundation of fossil fuels, and around 80% of the world's energy is provided by fossil fuels. So what are they? Here we've got a sun, and plants and animals that eat the plants, they grow and then they die, and their remains settle down on the ocean floor in this case, and they're covered by sediment. And then over a very long time period, and we're talking millions of years here, those remains form oil and gas and coal. And then humans come along and we dig them out, or we blast them out, or we pump them out, and then we get this stuff: oil, coal, natural gas. And what we then do is we burn them. And the reason we want to do that is because we want energy. So the whole convoluted pathway here is just to produce some energy. But in producing the energy, we produce a few other things. So CO2 is produced, as is water, and then there's these sulfur, nitrogen compounds and particulates. And so this is the smelly stuff, the nasty stuff that can cause things like asthma and lung cancer. But anyway, this convoluted pathway just to get some energy, which, by the way, we now have the ability to bypass all of that with solar. And just as an aside, this is where I ask the audience, guys, what do you reckon? So this is a logging truck which carries about 25 tons of biomass. So let's take that biomass, let's bury it in the ground for about 5 million years, and we'll dig it out again. It's formed petrol, which we have to refine to use. So how much petrol do you think 25 tons of biomass actually produces? Anyone? And the answer is 2 litres. So 25 tons of biomass creates about 2 litres of petrol. It's massively unsustainable. Massively. But anyway, this is fossil carbon, and fossil carbon is part of the carbon cycle. So carbon is stored a lot of different ways in our atmosphere, in our world. It's stored in our atmosphere, in our ocean, in our land. And before the Industrial Revolution, the carbon cycle was quite stable. So apart from the odd like volcanic eruption or massive bushfire that injected a lot of carbon into the atmosphere, this was all quite stable. But now what we're doing is we're taking carbon which has been stored in the ground a very long time, and we're putting it into the atmosphere by burning, essentially. And Earth will deal with this the way Earth normally does, that carbon will get dispersed through the oceans, the land, etc. But the problem with that is that it is changing our environment quite quickly, and everything that lives on Earth is adapted to a certain temperature. And when that temperature then starts moving into the warmer region, we don't adapt very well. It takes a long time for us to adapt, like humans as a species and other species. And so what we really need to do is to stop the cycle and to get our energy a different way. So we have the ability to generate energy now from what they call renewable sources or clean sources or zero carbon or decarbonized, lots of different terms. But that is essentially cutting off that carbon, that fossil carbon cycle, and using solar or wind or geothermal waves to create your energy. So the whole point of this is that it stops adding to this, this blanket of CO2 in the atmosphere. Okay, so I've talked a lot about CO2, and that is the main greenhouse gas. And it's the main one that humans produce. So this is an example here of different greenhouse gases globally emitted. And you can see carbon dioxide is the main one, but it's not the only one. We have got a few others. So the next biggie is methane. So when we, the humans, fart, we produce methane. Not very much, but ruminant animals, so those are the animals with lots of stomachs, they produce a lot more methane than humans. And it's generally burped out as opposed to farted out. So cattle produces a lot more methane than sheep and deer, and humans intensively manage cattle. So we've had this quite big increase in methane there. We also get methane from burying organic waste. So organic is things like food scraps or garden clippings. So we bury that in the landfill. When that decomposes, it produces methane. The next one we have is nitrous oxide. So when nitrogen fertilizers are spread on the fields, a portion gets used by the plants, but the rest gets converted into nitrous oxide. And also when you've got your cow pooing after eating nitrogen-rich food, that is also a source of nitrous oxide. So the main sources are from agriculture. fertilizer and for manure. Then we have this range of fluorinated gases. You can see it's quite small, and that's they were used for a raft of industrial things. You're probably most familiar with refrigerants. I've got some examples here of different fluorinated gases and their uses. So we've got a whole bunch of greenhouse gases here, and some are more warming than others, and they are in the atmosphere for different lengths of time. So it was really hard to compare all of these greenhouse gases with each other because they're all so very different in terms of their lifetime and their warming. So what they do is they all make them equivalent to CO2. So this is a term which you might have seen before, CO2e, which means CO2 equivalent. So it just made things equivalent to CO2. So instead of trying to add up some apples and some lemons and some oranges, you're just adding apples, equivalent apples, as it were. And the way that they do that is they look at the gas, how warming it is, and how long it will hang around for. And as an example, if you think about CO2 like one blanket around the world, just one, so 1 ton of CO2, say, is one blanket. For instance, methane, it's more warming than CO2, but it doesn't stay in the atmosphere for as long. It stays in the atmosphere for about 10 years. But one issue with methane, which not many people realize, is once it decomposes in the atmosphere, it actually produces CO2. So it's like the double whammy of methane. But anyway, so methane, it's more warming, but it doesn't hang around for as long. So it's kind of like having 25 blankets around the world. So you've got 1 ton of CO2, one blanket, 1 ton of methane, 25 blankets in terms of how warming it is. Nitrous oxide, 300 blankets. And then you get into something like sulfur hexafluoride, which is pretty common in transformers and circuit breakers and semiconductors. And that is about 23,000 blankets around the world. It has a big impact on warming. Okay, I'm going to stop there, and my next talk is going to be on carbon footprint. Thank you all for listening, and tune in if you want some more information.